I think we can start, or yeah. Now, Jürgen, say something.
Pardon?
Say something. 1, 2, 3. Okay, it works.
Yeah, 1, 2, 3. Yeah.
Okay, it works. So I would like to welcome Jürgen Braun, who is also from Munich. So he's in the group of Hubert, and he will speak about the relativistic theory of ARPES. So more generalized what I was showing you at the beginning. So Jürgen, you have 1 hour and 20 minutes, then hopefully a lot of questions. And I will turn off the video here and the microphone, so we will not hear us otherwise, because there is then feedback. So and then at the end I will then turn that on so that you can hear the questions. So thanks. So let's start. Now you can
Okay, yeah, then, yeah. Hello, good evening, everybody. So, first I thank, of course, the organizers for inviting me here to give a lecture in the summer school. And the title of the lecture is Relativistic Theory of ARPES. Well, I will start with an introduction of the conventional ARPES theory, the one-step model of ARPES and also of inverse photoemission. And then I will show application here to simple metals, to ordered and disordered alloys, topological insulators. I will talk a bit about temperature effect in photoemission and the extension to high photon energies. And the second part of my talk, then I will come to the time-resolved ARPES. Again, I will sketch the theoretical aspect, and then I will show the end some applications to simple ferromagnetic systems, and then give a summarize and outlook. Well, as you can see here, the history of the one-step model is nearly about 60 years. It started in 1965 with the angle integrated photoemission, the so-called three-step model, were introduced by Berglund and Spicer, where the excitation, the transport of the photoelectron and the emission through the surface barrier were handled in 3 different steps. This was, of course, an incoherent description of the photocurrent. And so some years later, a lot of people started with many-body theory of photoemission, like current correlation function, or based theories based on the Green's function method, time-dependent Green's function method. And the problem with this was at times that all these many-body theories, like Kalish-Green's function theory or current correlation function and so on, were at least untractable many-body theories, and one was not able to calculate photocurrent from real systems, even not from copper, a simple metal. And the situation, then changed beginning of the 80s. Henry, Leach, and others introduced a so-called dynamical Ansatz, is based on multiple scattering theory, and with this and the numerical implementation, which was also available at that time, then the photoemission becomes a theory which could be applied to simple metals first time. Only 1 year later, the theory was extended to disordered systems by alloys, or substitutional alloys by Durham. And then some years later, the relativistic photoemission started, first for non-magnetic materials. That means the spin-orbit interaction was introduced in the photoemission. And the main aim was to calculate with circular polarized light excited and spin polarized electrons. 5 years later, about 5 years later, the full potential photoemission was introduced to better handling of complex structures here and adsorbate systems. And then around 2000, the fully relativistic photoemission theory was developed. The key word is here the magnetic dichroism. There were also a lot of authors involved in this. And then up to about 2004, several extensions of the fully relativistic photoemission were developed as a combination with the DMFT the CPA, photocurrent for disordered alloys, was introduced in a fully relativistic way. The photoemission theory was extended to high photon energies. Phonons, vibrations were introduced, temperature-dependent photoemission, and last but not least, around 2015, then the time-resolved photoemission was developed. Well, here's an overview given what can be done nowadays. So here the KKR package written on the top allows LSDA electronic structural calculations or combined with DMFT or LDA plus U in the correlated materials. All these calculations are fully relativistic by use of the Dirac formalism, and the CPA could be applied for disordered system. All this was explained in the last talks during the week. And the potential input could be a spherical potential, but also now a space-filling potential. And typically, so the photoemission is used as semi-infinite half space. That means the tight binding mode of the KKR is applied. That gives a green function via multiple scattering theory, but still as input for the photoemission, we need here not the full Green's function. Instead, we need the single-side scattering matrix and the single-side wave functions. And then the photoemission can be calculated, and this for time and temperature-dependent angle resolved, ultraviolet photoemission, but also X-ray photoemission, and this for arbitrarily ordered and disordered and or correlated systems. Well, I'll start now with the theory, the theoretical description of the conventional time-independent photoemission theory. And the starting point here is always given by Fermi's golden rule. So we have a squared of the matrix element, the delta function guarantees the energy conservation, and what we have to do is to define or to formulate explicitly the final and initial state of the many-particle system and the interaction operator. This is shown here in the second quantization with a single particle matrix element. This delta is nothing else than the final state, which is used as a time-reverse split state. I will show later on. And the interaction is typically given in the dipole approximation, here the momentum operator times the constant amplitude of the vector potential and then some initial state. And vice versa here in the inverse photoemission case. General, it is very important here that the interaction of the photoelectron with the rest system is neglected. Otherwise, one gets not a reasonable formulation of the initial and final state. This means that we use a so-called sudden approximation, which tells us nothing else that the excitation of the photoelectron is so fast that the rest system doesn't, that the photoelectron feel the relaxation process, cannot feel the relaxation process of the rest system. And in this case, we can formulate this final state as simply as a direct product of an excited n-1 particle state with a creation operator of the photoelectron. The initial state is then simply given by the ground state, available by density functional theory, and again here vice versa for the inverse photoemission case. So now we can use these quantities and put it in Fermi's golden rule. That gives this transition probability here shown with in the middle here with a product of three operators. This seems to be hard to calculate it, but if we use the anti-commutator relations for the fermionic operators shown here, then we can recalculate this product and bring this operator AF from the left to the right side, that is shown here with a delta function. And due to the use of the sudden approximation, then we have AF acting on psi0, and this is just what the sudden approximation tells us. The electron is not present in the initial state, and this expression is zero. So only this term survives. And this brings us then to the so-called spectral function calculation of the photocurrent, here with a matrix element and this function in between, which describes the initial states, and this is the so-called spectral function here, shown by these formula. Then we use the next step, the connection between the so-called retarded one-electron Green function and the spectral function. This is simply the imaginary part of the retarded function is a spectral function, so we can put in here in the formula for the photocurrent. And then at least last point we use here the operator representation, and then we end up with a photocurrent formulation that was first introduced by Penry. But I have to say, Penry's idea was that the initial state should not be described here by the retarded one-electron Green function. That is a problem, because the retarded one-electron Green function fulfills the Dyson equation with a complex self-energy, sigma, depends on the energy. So Penry neglected this sigma, and this means he used, instead of the one electron Green function, the retarded one particle Green function, and this is then the standard formulation of the so-called one-step model in photoemission. Then we can bring this to the space representation and go to the relativistic case. And the relativistic case here means that we have here the spectral function is given by a 4x4 matrix, and the final state is given by a 4-spinor, and the interaction operator is here shown in the relativistic representation with the relativistic alpha matrix and the constant amplitude of the vector potential. Important, I will show in a minute some examples for this, for the so-called dipole selection rule. This means we calculate an angular matrix element between initial and final state, and this gives us this integral with the spin angular functions. The spin angular function itself are given as a product of the Gordon coefficients here of spherical harmonics and the Pauli 2-spinor. If we calculate these expression, which can be done analytically, then we get the relativistic selection rules instead of the non-relativistic case where we have the quantum number L and M. We have here the new quantum number kappa, and kappa could be plus minus 1 or kappa plus kappa prime is 0. And for the mu quantum number, where mu is nothing else than the magnetic quantum number plus a spin quantum number, we have the dipole selection rule mu plus mu prime is 0. This gives us the typical matrix, so-called matrix element effects. I will show you some examples in a minute. But still, we have to define the other quantities. The initial state here given in the spherical representation with the radial components, the greater and the lesser ones. And here with spin angular function, these are two quantities with two spinors here, so at least we have in general here 4 spinor. And in the valence band case, we have a spherical coefficient. The spherical coefficient for a single cell, which is shown here, is corrected by the so-called Camber lattice matrix. And this Camber lattice matrix, this expression 1 minus x in order minus 1, is responsible for all multiple scattering processes within a certain layer of a semi-infinite stack or a half space. And the coefficient, the spherical coefficient itself, is more or less a sum with some coefficients, and here we have the plane wave amplitudes plus minus, u plus minus, and this is the plane wave coefficients of the final state. And last but not least, we have to recalculate the dipole operator. This, I guess, was also shown during this week. One can apply commutator and anti-commutator rules to recalculate this operator in the so-called nabla V form, with the potential here and the nabla operator. And typically all the other contributions are neglected because they are orders of magnitude smaller than these two contributions here, the non-magnetic ones. So now we have all ingredients, and then we can in principle calculate the photocurrent. And first example here I want to show concerns the ARPES calculation from a topological system. And I compare experiment versus theory. The experiments were done in Friedel-Reinhardt's group here in Würzburg, and they're excited here with S-polarized and P-polarized light. with 6 eV photon energy and found in the spin polarization pattern red-blue construction. And if they excite with S-polarized light, but still if the excitation is done with linear P-polarized light, it changes from red to blue to red. And this is because of the excitation of different orbitals with odd or even symmetry. These dipole selection rules are differently excited. This is sketched here. The p-pole case, where mainly the 8z component of the vector potential is involved. And this means more colloquially that mainly, say, for example, pz orbitals are excited, and with s-polarized, so that the light is parallel to the surface, then mainly px and py orbitals are excited. And here's a calculation that's seen in comparison to the experiment, and this is a nice agreement. So we have again this change from red to blue, here red to blue and blue to red. This is not completely symmetric, and that is because here in the p-polar polarization is not fully p-polarized. Instead it is about 45%, so a mixture of s-polarized light is in. A second example concerns the intensities I want to show. This is ARPES, the ARPES calculation at 43 eV for the tungsten 110 surface. Again, a comparison between experimental data from the Markus Donat group in Münster, and then the calculations here on the bottom. And the calculations were done for the 3 high symmetry directions on the tungsten 110 surface, here with p-polarized light and with s-polarized light. And I guess we get a nice agreement, and in addition we can show that the intensity pattern are completely different due to the excitation with p or s-polarized light. And as a benefit, we found a highly anisotropic D-like surface resonance. It looks more or less like a topological state, but it isn't, because of the gap structure. I will show later on what this means. And then I come to the multiple scattering. We have to define then all the types of the photocurrent. I guess this slide was also shown. So we have a single part of the photocurrent, the excitation of a single atomic cell. We have in addition a so-called intra-layer part to the photocurrent, which respects all multiple scattering events within a layer, and this is managed here by this Camber X matrix. And as a last contribution, or the third contribution, we have a multiple scattering contribution between different layers of a semi-infinite stack. This is so-called the interlayer contribution. And if we take special care of the surface, then we add an additional surface layer to the stack of layers, and this gives us then a fourth contribution, so at least there are 4 contributions to the photocurrent. And here in more detail is shown that what means the multiple scattering within a layer. So here is a formula given for the layer scattering matrices. So we have 4 of these matrices for transmission from left to right, for transmission from right to left, and for reflection from left to right and right to left. And here you can see the single side scattering matrix. This is the input from the KKR electronic structure calculation. And here this expression again is this 1 minus x in the order minus 1. This is the Camber matrix, and the Camber matrix sums up to infinity all these multiple scattering between different atoms within a certain layer. I said we have a third contribution, the so-called inter-layer contribution to the photocurrent. So again, this is handled by multiple scattering. We have to calculate the bulk reflection matrix of a semi-infinite stack of layers, and this is sketched here. So we look here to a layer 1 and a layer n plus 1, and then we sum up all possible scattering events. So the first could be a reflection here, then the second could be a transmission to the first layer, then a reflection at the second, and then again back, and then a higher order reflection pattern are seen here, and at least we have to sum up to infinity all these scattering events, and this results here in the formula shown here. And this infinite series means here we have more or less a geometrical series indicated here by the expression here in the brackets with the order -1. This could be developed as a geometrical series. So indeed then we have the scattering properties for a stack of 2 layers. This procedure, and here is shown the corresponding scattering matrix. Again we have 4 matrices for reflection from left to right, from right to left, and transmission due to a stack of 2 layers. And if this procedure is repeated, this is so-called layer doubling method in the multiple scattering theory, then at least we get the reflection properties of a stack of 1,000 layers or even more, what is necessary to get the reflection of a semi-infinite R-space. And this method converges if a small imaginary part is introduced, so a damping, and then we can calculate the final state as the next step. And this is shown here. So we start, we have here the bulk reflection matrix, we separate the first layer, we define the amplitude U0 in front of the first layer, and then means by multiple scattering techniques we have to calculate these 2 amplitudes, and this is shown here. This is also quite easy to do. We calculate the amplitude U1 plus simply by transmitting U0, reflecting, moving it back, again reflecting, and so on up to infinite order as I showed before. And if this amplitude is established, we have the formula calculated. Then we can calculate the amplitude U minus as simply reflected and the bulk reflected U plus and propagated by the propagator again here to the first layer. And this procedure can be repeated. So here the scattering amplitudes between the first and second layer. Then we separate the second layer from the rest bulk and calculate the amplitude U1 minus and U2 plus. And due to the imaginary part, the damping which is introduced in the final state, a so-called optical potential, then this procedure converges as the magnitude of the amplitude decreases tremendously over, let's say, 20 or 30 layers, and this defines then the photocurrent which has to calculate it from these 30 layers. And the sum of all these different amplitude together with the propagators defines then the time reversed split state. Oops. Yeah, and I want to show that it's possible to plot these wave functions to get an expression what happens there. I show here for the silver 110 the initial and final state wave function. Here the final state, because of the higher damping, the final state penetrates only by here. Even in the bulk sensitive case, where the optical potential is quite small, the bulk only up to 200 or 300 layers, whereas the initial state penetrates about 1,000 layers. But doesn't matter. In the photocurrent, we have to calculate via the matrix elements only the overlap between the initial and final states, and this means we can cut the photocurrent sum over layers up to an infinite number, which is defined at least by the final state. The rest of the initial state doesn't take care in the photocurrent. And here is seen the initial states and the bulk-like states in the surface sensitive mode, and surface sensitive mode means typically the ARPES regime. If we want to calculate a photocurrent with 15, 20 or 40 eV, then the optical potential is in the range of 2 to 5 eV, and then we can see here the final state is restricted to the first 20 or 30 layers, and so the photocurrent is surface sensitive, because the bulk, the initial state which penetrates the bulk up to 100 layers doesn't account for the photocurrent itself. And then The last picture here is a surface resonance shown, not a real surface state. It's a surface resonance, so has a certain bulk contribution. And here in the surface sensitive case, it's only about the wave function decreases tremendously here over the first 5 or 6 layers. And in the surface bulk sensitive mode, of course, we have done several layers more. So this can be checked, what happens with the initial and final state wave functions, by simply plotting these quantities. And yeah, the last step is we have to calculate the photocurrent itself. And nowadays, since some years, this is done in the so-called spin density matrix formalism. And this is because the spin density matrix formalism gives us access to the complete spin polarization vector of the photoelectron, not only to the intensity, but to all 3 components of the photoemission spin polarization vector. This can be done if we define a matrix. It looks here like Penry's formula, with the final state here, the interaction operator, the one particle Green's function for the initial state, again the interaction operator, and the final state. But still, in the normal case, spin polarized case, this quantity is calculated only twice, with spin half, and spin half, minus half. But we need here a 2x2 matrix, so we have to calculate 4 times the photocurrent. This is the default modus in ARPES, that S-pol is equal 4. This parameter, if you want to do numerical calculations. And then we can define the real spin density matrix here by this expression. And this is a 2x2 matrix. And the photocurrent intensity is then given by the trace of the spin density matrix. The spin polarization is given by the trace normalized by the intensity. If we multiply the density matrix as a Pauli spin matrix, sigma x, sigma y, and sigma z, and at least we get the photocurrent in a certain direction, the majority and minority part, and this is all what we want to have. What we in addition need, as I said, electronic structure input from the KKR, electronic structure calculations, the wave functions, and the single-side scattering matrix. But what we also need is a geometrical arrangement. This is sketched here in this cartoon. So we have a semi-infinite stack of atomic layers with a coordinate fixed on the surface here with the incoming light and the outgoing electrons. And due to the optical potential, the initial final state decreases over the stack of layers. The atoms here, or single-side cells, can be handled as spherically symmetric potentials, as a Martin approximation. And as I said, nowadays we can use space-filling cell potentials to calculate the electronic structure and single-side scattering matrix. And as I said before, we take special care of the surface in the photoemission calculations. That means we put an additional layer on top of the atomic stack of layers. And this is a one-dimensional potential here. There's a model barrier, but it respects the long-range 1 over set behavior, and this allows us also to calculate the so-called image state. I will come later on to this. And we have an additional benefit. This goes to a idea from Penry and co-workers, that we can calculate this determinant, which is nothing else than the product of the reflection matrix of surface and barrier. And if a surface state or a wave function is trapped because here is a band gap in the volume band structure, then the wave function cannot really penetrate and is here trapped in the front of the surface. And this is just the definition of a surface state. So if we calculate this expression, this also standard output in the KKR photoemission calculation, we can identify surface states. And if this expression gives a minimum, we are able to follow also the surface resonances, what is not so easy because the typical surface resonances have a bulk contribution, not really available from initial state step calculations or else. So if we have all this, then we can do the calculations we want. And here I show the different surface and bulk electronic structure which could appear. So the 2-dimensional electronic structure, we have the bulk states dispersing, we have surface states in layered systems also we can have quantum world states, and surface states are divided in two parts. The bulk-induced surface states, S-like surface states are called Shockley surface states, and D-like surface states are called Thumb states. And of course we can have surface resonances, not real surface state because of the pronounced bulk contribution. And at least we have, due to this model barrier we have introduced, this long-range behavior, the so-called series of image states. And this, of course, why we use a model barrier, because the reason is in the LSDA, the electronic structure or the density decays exponentially, but not with 1/set. Yeah, that brings me to the next example here. I show the projected bulk band structures here along gamma M and gamma K direction for the rhenium 0001 and osmium 001 surface. So we have here hexagonal systems, and we see here the white regions, and the white regions indicate gaps in the projected bulk band structure, so no bulk gaps exist here as a function of the binding energy and the K value, K parallel value. And in this region we expect that different types of surface states and surface resonances could exist. And the more pronounced the gap, that the more the surface state probability is given. Then we can look to the spectra. Here calculated intensity and the Rashba component of the spin polarization in the models that we have here E versus K parallel diagram. And indeed here we found anisotropic D-like surface state dispersing in this gap, which was sketched in the last slide. And here's the Rashba component. You can see here the Rashba splitting, this red-blue, blue-red pattern. It's not so pronounced in the gamma M direction here, because the gap is much smaller, but still we have a gap here around the Fermi level, so we decide this is a surface state and that is not a surface resonance, but still a Thumb-like, because here we have these states. Then we can do another type of calculation. I showed the E versus K parallel calculation. What also can be done is a constant initial state calculation. So we fix the initial state, let's say at the Fermi level. Then we calculate the photoemission as a function of the polar and azimuth angle, so we get a complete surface plot, intensity plot, which is called negative SES, constant energy surfaces. And what we can do is calculate a lot of these surfaces as a function of the binding energy. This is shown between EF and binding energy of 3 eV in steps of 0.1 eV. So we have 30 of these CES pattern, and we can put together to a picture, so we get then the dynamical survey through the band structure up to 3 eV binding energy here. And if one looks here, the surface state appears here where the ring appears here. Then we move here through the surface state, and the rest are the bulk states. And it's more or less the same here on the osmium surface. But here, due to the pronounced band gap in the rhenium case, we have a real surface state here in the middle of the Brion zone. But here we have the surface, more surface resonance that appears here. Yeah. And second example, together with the corresponding spin polarization, is shown here for molybdenum 110. Again, the 3D ARPES calculation. It's excited here by S-polarized light at 21 eV. And again, in molybdenum there exists a small gap around the Fermi level, so also in this case we have a surface state which appears comes here now, this ring here. Brings me then to the next slide. Oh, sorry. So, a bit slow here. Yeah, so, okay. The so-called image potential states, as a type of electronic state which can exist on the surface because of the long-range image potential behavior. This is sketched here. So we have here a band gap, we have this long-range potential, here's the image charge, and at least here we have the wave function of the so-called first image state, the second image state, and get an infinite series at least at image states pinned on the vacuum level. And here is shown as an example the nickel 111 surface, majority spin and minority spin. The shaded areas indicate gaps in the projected bulk band structure, and here we see these image states dispersing here with a certain spin splitting, and here we have around the Fermi level bulk states and surface resonances of SP and D-like type. This can also be analyzed by using this determinant criterion. Yeah, but we can also look to Rashba physics not in the normal surface state, bulk-induced surface states. We can also look to Rashba splitting of the image states. And as a first guess, one would say, well, there could be no Rashba splitting because the image states wave function are far in front of the surface, pinned at the vacuum level. But it's not really true if we go to materials with high atomic number here, like iridium, platinum, or gold. Then we get a Rashba splitting that is quite small, not measurable at the moment, but is still present. Here for cobalt, as a reference, we see cobalt with a low atomic number, we can only see the exchange splitting, but not the Rashba splitting. But we can increase atomic number by looking to the Rashba image states on bismuth selenide. And here, due to the even higher atomic number of bismuth, we get a spin, a Rashba splitting here of the first image state. This is comparable to the copper 111 Shockley state, and this Rashba splitting for the copper 111 Shockley state was measured, so this should be also measurable. Yeah, and the last type of electronic states appear as the so-called quantum well states. I show here as an example system 50 monolayers gold on the rhenium 110 surface. And what we can see here, the intensity pattern and the Rashba component of the spin polarization. So we have here the surface state dispersing here. But in addition to these bulk states, we have a series here shown better even here in the spin polarization pattern, or here a series of quantum well states which appear due to this layered system. They are established, and they, of course, confined here by the thumb-like surface states. They want to disperse further to higher binding energy, but are hindered here by this surface state. Yeah, the next point I want to discuss then is the relativistic one-step model for alloys at t = 0. There was also talked about during the week about this point, but still I want to introduce here again the photocurrent and the space representation, again the relativistic notation here, and we call this ACBL coherent spectral function. And what is the difference? Due to Durham, it turned out that the one-step model of photoemission with these 4 contributions at least could be established, except that due to the configurational average in the coherent potential method, additional contribution appears here, the so-called incoherent contribution. And this is a DOS-like contribution due to the configurational average, where here we have the multiple scattering contribution, the atomic contribution, and again the surface contribution. And this is here shown in the spherical representation, the four contributions here, with the set matrix and coefficients of the final and here initial state, spherical coefficients. But here in between, we have these so-called set matrices and that inhibit all the radial and angular matrix elements. Yeah, example is here shown for ARPES calculation on such a disordered alloy. And the interesting question was, what happens if we study the interplay of spin-orbit interaction with exchange interaction? Therefore, we decided for a alloy, nickel copper, where nickel is ferromagnetic and gold, on the other hand, has a high atomic number. Then we look here to the famous Shockley surface state on copper with a low nickel concentration of about 10%. And here we can see more or less a Rashba split surface state is established. But still we increase here the concentration of nickel up to 15%, some distortion appears. And if the nickel concentration increases here up to 25 or 30%, then the dispersion of the surface state is completely distorted up to a high nickel concentration, where no longer the SOC, the spin orbit splitting or Rashba splitting is visible. Instead here we have then the ordinary exchange splitting of the surface state. So it's quite a nice example. And I want to show a second example of a alloy. There's a nickel, again nickel, a nickel palladium alloy. Here on the top is shown the spectral function for nickel 70 palladium 30 concentration alloy. And the LSDA, we show here some band smearing. This is of course the broadening of the states due to this disorder. Means the self-energy of the CPA. Then if we apply the LSDA plus DMFT method, because your nickel is ferromagnetic, then we get in addition smearing due to the DMFT self-energy. We get a band narrowing of the D bands shifting to the Fermi level, and all these effects are visible. And then we can calculate the photoemission under these conditions shown here on this transparency. Here's a series of spectra shown. It's a function of the photon energies from 20 to 40 eV. In the middle you have the experiment. Here's a surface resonance existing, and we see here the two peaks are quite narrow. If we look here through the LSDA, we see that much broader the peaks. If we use then the LSDA plus DMFT electronic structure input, we are much closer here to the experiment. The surface resonance is present, but still due to the band narrowing I mentioned before, the bands shift due to the Fermi level, then we are much closer here to the experiment. So again here we have more or less quantitative agreement, even in this quite complicated case. Yeah, the next part concerns then the soft and hard X-ray ARPES. Yeah, the motivation of course is one wants to have a higher bulk sensitivity. This is shown here by this universal curve. So one can go to low photon energies like laser ARPES, then the bulk sensitivity is strongly enhanced. But one can go also the other way, from soft X-ray to hard X-ray, and then we can expect that we can look much deeper into the bulk and study the bulk properties even for buried layers and so on. Yeah, but for this purpose we have to modify our multiple scattering theory. I show again here the scattering matrix for a single layer. Here with a single side scattering matrix and the Camber matrix. And the benefit is that the higher the photon energy, the more we have, the more forward scattering appears, and the scattering, the multiple scattering within a layer decreases tremendously. And this means for high photon energies we can simply set this quantity to 0. So that 1 minus 0 is simply 1, and this is all what we have to do to go to higher photon energies and get then a quantitative description of the photocurrent in the Huxley and soft X-ray case. So it's not much to do from theory, only have to neglect the scattering matrix. Yeah, the first example is your soft X-ray ARPES, shown on rhenium and on silver 100. And here is shown again a constant energy surface calculated more or less at the Fermi level. And the interesting point is here, if one looks more close here to the intensity pattern, one can see here that yeah, the structure here is not symmetric to k par 0, and this is due to the photomomentum. In ARPES, the photomomentum is so small that it can be neglected. But if we go to photon energies of several hundred eV or even keV, then we get a pronounced shift of the spectral intensity in the direction of the photomomentum. And this here shown at 630 eV, and then even at higher energy, and you can see that the shift increases. And here the second example is the silver 110 surface plotted here along the gamma K direction, about 550 eV, excited by circular polarized light. And here we neglect the photon vector dependence, and on the right we included this. And also you may see that we have here the pronounced shift, the asymmetry around k parallel 0, where here is more or less 0. And the formula still for the k vector of the initial and final state here given on the bottom, and here enters the photomomentum vector, and if this is really small, then the pattern is symmetric. But if we go to high energies, then this number here increases this quantity, so the influence is significant. This is a typical effect in ARPES, soft X-ray ARPES, and so on. As a next example, I show again the tungsten surface state, which I have showed before, but still at high photon energies. And I said, due to the strong bulk contribution of this surface state, it penetrates about 6 or 7 layers of bulks, atomic layers. One could expect that even at high photon energies, that these structure or intensity structure survives. This is not the case if you look to a simple Shockley state, for example. If you increase the photon energy, then the Shockley state or real surface state decreases tremendously in energy, is no longer visible. But it's not here the case if we look to surface resonances, even visible at high photon energies here in the Huxley's regime. So this state really survives due to the relatively high bulk contribution. And here on the bottom is shown the spin polarization, corresponding Rashbach component. Yeah, if we go even to higher photon energies, I guess it's also shown during the week. Here, hard X-ray ARPES from tungsten surface along gamma N direction. And the problem here is, the spectra were recorded at low temperature, 30 K, to avoid phonon excitations, because phonon excitations induce strong smearing effects, and this makes really, in the principle, not really possible to detect here the dispersion in the D-band complex, for example, whereas the S-band, this is great dispersion, are clearly visible compared to the free electron theory. But the phonon excitation, this is a problem, induce relaxation of the local dipole selection rule. I will show in a moment. And this means that we have really need for ARPES theory at finite temperatures. Yeah, how to do? There's an old article from Chevchik. He analyzed it as the first work. So in 1977 was this published, and what Chevchik found is that the photocurrent can roughly be divided in a direct part, here with a Debye-Waller factor multiplied, and in an indirect part. And the indirect part is a DOS-like part. So if the photon energy is increased, then the direct part decreases in energy, and at least what is still alive is the indirect part, and this is called the so-called DOS limit, where in the direct part all the multiple scattering is involved and all the dispersional features, and if these vanish, then we have only a DOS-like spectrum. And the actual situation before we started with our work was that only the Debye-Waller factor was considered via a temperature-dependent single-site matrix. But still, there is a need for a temperature-dependent multiple scattering theory included in the one-step model description. And I guess this slide was also shown more or less, so I have not too much to talk about this. The idea of Hubert Ebert, at least. So the suggested that the CPA averaging can be applied to dislocations, atomic vibrations. So the atoms dislocated at a certain temperature, so we have this set of dislocations. We can define a set of dislocation, different types of locations. Then we can define a probability function, which represents the discrete displacement. And then we can do a configurational average in the CPA sense. And then we have a pseudo-alloy, and this is called the alloy analogy model. This means at least we use the CPA theory, which was established before for the CPA photocurrent, but still instead of different components, we use different displacements on average over the different displacements. No. Sorry. Yeah. And this at least gives then an average photocurrent, which is temperature dependent. Here we have the angle resolved photocurrent on the top with atomic contribution, the surface contribution, the two multiple scattering contributions, and this incoherent contribution, but it's now T-dependent. And we can also define the angle integrated photocurrent, and the angle integrated photocurrent consists only of the atomic part, the surface part, and the incoherent part. So the multiple scattering part is zero. And yeah, if one looks then to the difference, then we can say, aha, the angle resolved photocurrent enters the angle integrated photocurrent or DOS-like photocurrent is called the XPS limit if the multiple scattering contributions vanish, go to zero. And this is shown here as an example for the atomic contribution. We're given here the spherical representation with the final state coefficients, and here in between the set matrix, the angular and radial matrix elements involved. And the averaging is at least like we use a dislocation matrix for every type of dislocation. And the average means then we multiply here the T equals 0 matrix element with this U matrix, and this gives a temperature dependent matrix element. And this temperature dependent matrix element, due to this averaging, I call it U averaging, gives a relaxation of the local dipole selection rule, and this effect is then an energy-dependent smearing due to redistribution of spectral weight. Well, that is here shown on the right side. We compare here experimental and theoretical data for EDC cuts for tungsten 110 at 870 eV, with roughly along a gamma n direction. And you can see four features here, 1, 2, 3, 4. At 300 Kelvin, the temperature is increased. And at about 800 Kelvin, here the so-called DOS or XPS limit is reached. More or less all dispersing features are vanished due to the huge amount of phonon excitations. If we look here to the theory, if we use this averaging, then we are close, as the solid lines are close to the experiment. That is really fine. If we compare them with the CPA calculation at T equals 0, then we can see we have sharp peaks even at high temperatures. So this works quite fine, but it's not the complete story. In addition to this energy broadening, we have also K-dependent broadening. And this is shown here in form of MDC cuts for the tungsten 100 surface, again at 870 eV along the gamma n direction. And here the experimental data show that if the temperatures increase, then the dispersion-like features are smeared out. And if we look to our theoretical calculation, where only the energy-dependent smearing is involved, not much happened. So this is a discrepancy still, but we can do it better in introduce vibrational modes of complete layers directed perpendicular to the surface. This is also, I guess, Jan told about this approach. Here's a simple example given here. If we look to this black curve, this is a theory where no K broadening is involved. The experimental curve is here in red seen. And if we induce vibrational modes between different layers, then we are really close quantitatively to the experiment. And if we compare this in E versus K parallel plots, then we are much closer to the experiment if we include both of these effects. Yeah, and the XPS limit is here shown again on a gold 111 surface. So here is calculated ARPES spectra and angle integrated spectra at 1 keV and at a temperature of 10 keV, and then one can see that here we have pronounced dispersional features in the angle result spectra, but more DOS-like features here in the angle integrated photoemission, which is still expected. But still, if we increase the temperature and do all these Evering procedures, then one can see that the dispersional features decrease, and even at 300 Kelvin, then the angle integrated photocurrent looks more or less as the angle result photocurrent. All dispersional features are vanished, and this means we have reached here for gold 111 at 1 keV at a temperature of 300 keV the DOS limit. If we look to higher photon energies, say at 6.4 keV, then still we need only a temperature of about 100 keV to reach the DOS limit. This is the general problem in the ARPES. So that brings me to the summary of the conventional photoemission theory. I can say the KKR package allows nowadays for fully relativistic split, ARPES, angle integrated, and also core level photoemission. Yet not the time to talk here about split calculations, but they also involve task. Use a task 1, then you can do split calculations, and this can be done for photon energies ranging from about I'd say 5 to 10 eV up to about 10 keV. The LSDA plus DMFT approach for the electronic structure combined with the photoemission allows then for quantitative analysis of spectroscopic data from correlated system. If we use the CPA plus photoemission phase method, then we can handle quantitatively chemical disorder in photoemission excitation. And last but not least, the alloy analogy approach allows them to handle thermal vibrations and spin fluctuations at finite temperatures. That brings me then to the second part of my talk, the theory of pump-probe photoemission or time-dependent photoemission. The formula here on the top is due to Frerichs et al. They first developed this transition rate, time-dependent transition rate, which indeed looks quite similar to Fermi's golden rule. With the squared of the matrix element between a final state interaction operator, but the difference is here we have a time-dependent initial state. And this works for arbitrarily strong pump pulses, so there's no perturbation theory here involved. The only approximation which is needed is a sudden approximation, again as in the time-independent case. So in the many particle state of the rest system, we exclude the high energy electron as shown here in the time-independent case, so that we have a excited state of the 1 minus particle system times at least the operator of the equation operator of the photoelectron. This is more or less the same, but the main difference here is in the time dependence of the initial state, and the time evolution, of course, of the initial state. This can be described as a function of the probe pulse with a time evolution operator. This quantity is shown here, the time ordered. This T means in front of the exponential factor time ordered time evolution operator. here with a Hamiltonian time dependent and the corresponding perturbation. If we put these quantities in a similar way as shown before, find the initial state here in this Fermi golden rule type formula, then we end up after some algebra applying in addition first perturbation zero in the probe pulse, but this is allowed because one can really assume that the weak pulse is that the probe pulse is weak compared here to the strong pump pulse, which is could be strong. So we can use first order perturbation theory and end up here with a transition rate, and it looks this expression looks quite similar to Fermi's Pendry's approach to the one-step model, here with a single-side matrix elements. Of course, we are time dependent in the time-dependent case, so we have the perturbation, the time-dependent, in addition an exponential factor, an oscillating factor. But the main difference to the time-independent case is that here appears one particle correlation system with the creation and annihilation operators, and here we have two time arguments. And this is the so-called lesser component of the Keldysh-Green function. And here we have really two independent time arguments. In the time-independent case, we had only the time difference here involved, and we have only if we have only the time difference, then we can apply a Fourier transformation, go to the energy representation, and then the lesser Green's function here reduces more or less to the well-known retarded KKR Green's function. But this is not possible in this case. We have here really a two-time quantity, and this makes calculation in the pump probe for real system again untractable for at the moment. But we can apply a similar trick that Fermi did. Pendry said we neglect the self-energy, the energy-dependent self-energy, and switch from the one electron Green function to the one particle Green function. We apply here a similar restriction that we only consider self-energies which depend on the time difference. And this means we solve the Cardanov-Bain equations on the Hartree-Fock level. And the result then is a coupled system of integral equations for the lesser and greater component of the Keldysh-Green function, which we can put with the Langren-Wilkins rules from the complex plane with complex times z and z prime on the real axis for t and t prime. And we end up, after some algebra, with this coupled system of equations for the lesser component and for the greater component of the Keldysh-Green function, here with in between the time-dependent perturbation. And the benefit, if one does this, for this coupled system of integral equation exists an analytic solution. And this makes it handleable, can be handled then. Yeah, this is shown here. The lesser Green's function in the so-called interaction-free case. Interaction-free case means the self-energy depends not on two independent time arguments. The lesser Keldysh-Green's function is given by the product of the retarded Keldysh-Green's function with the KKR Green's function, or with the imaginary part, times the advanced Keldysh-Green's function. And the analytical solution gives us a Dyson equation then for the retarded Keldysh-Green's function, which looks like here we have a single term retarded KKR Green's function, we have an integral with a perturbation, and then again we have here the retarded KKR Green function, but here at the end here we have the retarded Keldysh-Green's function. It means in principle we have to solve these Dyson equations self-consistently. This is hard to do. But what is easy to do is to calculate from the retarded Green's function the advanced Keldysh-Green's function. So these quantities are available. Then we have also available the lesser Calish-Green's function. And we can restrict. This is another approximation, but if we look to pump-probe experiments in the form of two photoemission experiments, then we can assume that both the probe and the pump pulse are weak, and that means we can put here in, instead of G plus, G0 plus. And here shown is the KKR retarded single particle Green's function with a multiple scattering and the single side part. And if we do this, then we end up by a relatively simple integral equation, not integral equation, but an integral. So we have here the single side term, and then we have here a product of the Calish-Green's function, the KKR Green's function, which itself, where in the middle we have the perturbation. And this, of course, can be done. This can be numerically implemented, and this allows us at the end to calculate in this approximation where the pump as well as the probe pulse are weak, the lesser Calish-Green's function, and gives access to calculations then to real systems. Yeah, here's then shown the one-step model in the spherical representation. We have the time-dependent photocurrent and the one-step description. Again here with the spherical coefficients of the final state. Of course, the final state again is a time-reversed speed state. Here's the angular matrix element. And here in the middle we have a time-dependent matrix element where we have here the radial part of the lesser Calish-Green function. Yeah, this brings me then to first applications. Inverse photoemission compared here with 2 ppE photoemission on iron FCC. Here we have calculated a series of image states, the first, the second and the third image state. And what we can see here, due to the spin-orbit interaction, we have not 100% spin polarization. Here we have the spin splitting, the exchange splitting, because it is a ferromagnetic material. But still here, what is normally assumed in the experiment, that both of these peaks are 100% spin polarized. But still in the calculation, ordinary inverse photoemission calculation, not 2 ppE, we find an incomplete spin polarization. If we look here to the corresponding experiments were done in the Martin-Reinhold group, we have here 3 monolayers iron and copper 100, and we see here the first image state with the spin splitting here, majority and minority part. Here is the second image state, and as one can see, this is a real Lorentz peak here, so one would not expect that we have an incomplete spin polarization. It looks here, spin polarization is like 100%, and it seems this is a contradiction. And the problem is that in inverse photoemission experiments, the resolution is only about 0.4 eV, that even with the spin statistics, it's not clear and not available or detectable if the spin polarization could be incomplete. That means it is assumed it is complete, and it seems so that it is indeed the case, because a 2 ppE, which is able to resolve the spin polarization, shows or indicates that it's about 100%. Yeah, then we can calculate it's really 2 ppE spectra using the complete formula. Using the complete formalism. Then again, we found here, yeah, the parameterization is here given by the probe pump pulse and probe pulse. The probe is here given with a photon energy of 6 eV. With a ferromagnetic system, so we can, in addition, compare LDA calculations versus LDA plus DMFT. Then we have here the first image state, here split it by about 50 millieV. This is quite nice compared to experiments from Waller and Forster group. They found about 60 millieV. and then you have this second image state, and if we compare then in addition the LDA with the DMFT, there are small differences. This could be expected because the image state are quite far from the surface located, so and pinned at the vacuum level, so correlation effects should not really pronounce in this state, but still one can see it is a small difference here. But we see again here the incomplete spin polarization because this is not really a Lorentz peak. So what happens there? I show here a series of spectra for cobalt 100, calculated with p-polarized light. Again, the first image state is here calculated, and if we calculate this as a function of the probe energy, pump is about 4.3 according to the experiment, and in the experiment they used quite low photon energies for the probe. It was about 0.5 to 0.7 eV. If we do the calculation in this parametrization, then we can see here, besides this shoulder here, it seems that the peaks are 100% polarized. There's no additional structure. But still, if we go to higher photon energies in the probe, then spectra looks quite funny. And enter here at about 7 eV, then we see here a pronounced component, so that one should expect that even in the 2 ppE photoemission experiments, incomplete spin polarization could be found if the measurements were repeated, but not with about 1 to 1.5 energy in the probe, but then have to go to higher probe energies. So at least there is no contradiction. It seems indeed a problem of the probe photon energy. Yeah, so far we have only looked to the quasi-static feedback of the system, and quasi-static feedback of the system means in this calculation only a static potential from the LSDA electronic structure calculation was used, and the only time dependence here is due to the pump and the probe pulse. But still the formalism, as shown here, allows for the introduction of self-energy or potential which depends on time. Not on two-time arguments, but on one-time arguments. So at least we can introduce a time-dependent potential in addition to the time dependence coming from the probe and pump. And this is possible nowadays because the so-called ELK code is now available. And with the ELK code solves the time-dependent Hamiltonian in the framework of time-dependent density functional theory. And here is shown an example here with external time-dependent field. Here's a pump pulse given with a Gaussian profile and the other parametrization. And this gives at least a time-dependent potential for certain time steps, but it gives also occupation numbers here in the ferromagnetic case, spin up and spin down occupation numbers, shown here BCC iron 110 and SCC cobalt 100. And here, before the pump acts, really, we have more or less here the Fermi distribution here for iron and cobalt, and then we get occupation here in the unoccupied regime. And if this would be included, where we work at the moment on this, it's nearly finished the implementation, then one would expect even better comparison with experimental data. But still, before one can do ordinary photoemission, this is shown here, because we have a spin-dependent potential, the occupation numbers, we can calculate with a conventional one-step model a spectrum, the spin-split surface, spin-split states. But if we use in the next calculation the time-dependent potential concerning to time step here of 15 femtoseconds, then one can see that the spectrum slightly changes. changes in as well as in the spin splitting, also in the relative intensities, according here to the magnetic moment which develops here as shown on the top. And one can put this together to a E versus K plot. This is here shown more or less on the last transparency. We have here a minority spin spectrum in the E versus K par modus, majority and minority, and then put both spin channels together. Then we have here at least the time-dependent band structure due to the excitation by a pump pulse. And this brings me to the end. So summary and outlook here for the time-dependent ARPES, a generalization here of the one-step model of photoemission to the time-dependent case was worked out, and this is based on the Kalish-Green function approach. We have first applications shown, simple ferromagnetic system, which are in quite good agreement with the corresponding experimental data. Yeah, we plan, of course, further development in time-resolved photoemission and we remove of the linear approximation, so want to calculate the Dyson equation self-consistently. And what is nearly finished in the implementation is the use of the time-dependent potential as well as the time-dependent occupation numbers. This gives it then access to relaxation processes and dynamical correlations. And we plan, of course, further application to ARPES and time-resolved ARPES for more complex, interesting systems like topological insulator, ultra-fast demagnetization could be handled, and of course other types of time-dependent experiments, for example, like time-dependent SAS can be handled. Yeah, this brings me to the acknowledgement, and this is my last transparency, and I thank you for your attention.
So, thanks Jürgen. Can you hear me now?
Yeah.
Yeah, good. So, questions? People are tired already. But Didier is standing up, so wait a second. Didier comes.
Yes, Jürgen. I didn't, in the case of the temperature-dependent photoemission, I didn't quite understood what you mean by relaxation of the dipole selection rules.
Yeah. The dipole selection rules, the normal dipole selection rules are, I can say in a non-relativistic version, is L plus minus 1 and these type of selection rules. If phonons excited, then the dipole selection rules are relaxed in the case that L plus minus 2, L plus minus 3 and transitions like this become possible. And this is simulated by multiplying the dislocation matrices from the left and from the right side in the sense of the CPA average with a dipole matrix element, with a radial and angular matrix element, where still the dipole selection rule is established, but after multiplication from left and right with these displacement matrices, then the matrices are full in the sense, and the dipole selection rules are completely relaxed or disturbed and no longer exist.
Okay, thanks, Jürgen.
Yeah, John? Just a second, Jürgen. John.
Okay, hi. So I have another question on the finite temperature ARPES. In this Shevchuk work, he always uses correlated Debye-Waller factors. I mean, you seem to ignore correlations between the atoms. How important is that approximation?
I know what you mean. I forgot to say it. Shevchuk also showed that the higher the photon energy, that's lesser the correlation. This is a sine-like function. This method works not for low photon energies. It means in the normal ARPES regime, the vibrations are highly correlated, and we cannot do this procedure. But if we go to Huxley's energies, high photon energies, then the correlations are more or less uncorrelated. is, yeah, you mean this one here, I guess, yeah. This was found by Shevchik in his paper, that the amount of correlation tremendously decrease with the increase of the photon energy. And then when we are in the higher soft X-ray regime, let's say 1 keV, or even in the hard X-ray regime, then really can assume to a really good approximation that the correlations are, that the vibrations are uncorrelated. So that you're completely right that this formalism would not work in the ARPES case. In the ARPES case, then the correlations, the vibrations, dislocations are highly correlated within the typical layer, the single layer. One can think about to use a non-local CPA approach, but we discussed it in our group. It's not really manageable. That is a quite different task, yeah. But for high photon energies, one really can say that, no correlation is present in the vibration.
Well, just a short comment. So you see it in data as well that we get only the energy dependent broadening, but not K. So
yeah,
along the K. So for a certain K, this can be bit. The trick is, as I showed for the surface, it is kind of correlated vibration. The surface, you have a different vibrations than the bulk. One could try to correct it this way, but it's not the right. You are right. I mean,
that's indeed is at least this broadening is caused by two different effects. This is energy broadening. This energy broadening is due to the relaxation or the distortion of the dipole selection rules, the smearing. But as I showed in the MDC, there is an additional mechanism of broadening, and this is can be simulated by vibrations of complete layers against each other, so breathing modes perpendicular to the surface. I guess Jan showed also a picture, Nick, in his talk that Nick respect with these type of dislocations, which could be also introduced in the alloy analogy model, then they get much better comparison than what the smearing concerns with the experimental data.
Okay, thanks. Some other questions? If it's not the case, the rule is as before. If you have special questions to Jürgen, just let us know. We will organize some session. And thanks, Jürgen, again. So we now go for dinner.
Yeah, normally after dinner we have a students' question session. So if nobody of you has any question,